In the last video, we talked about the definition of a Laplace transform. And we used that definition to determine that the Laplace transform of 1 was 1 over s, so long as s is greater than 0. And the Laplace transform of e to the at is equal to 1 over s minus a, as long as s is greater than a. And the Laplace transform of sine of bt is equal to b over s squared plus b squared, as long as s is greater than 0. So now we're being asked to find the Laplace transform of 11 plus 5e to the 4t minus 6 times the sine of 2t. So the nice thing about the Laplace transform, just like with integrals, which should make sense because the Laplace transform, the definition of it is just a certain integral, we can do two kind of nice things. One is we can take the Laplace transform separately, of each term separately. Also, we can bring a constant out in front. In other words, the Laplace transform of 5e to the 4t is this, the Laplace transform of 5e to the 4t is going to be equal to 5 times the Laplace transform of e to the 4t. And that's the same type of thing that we're used to being able to do in an integral. We can take a constant out front, and we can take the integral of each term separately. All right, so let's do that to find the Laplace transform of this whole thing. So here we have the Laplace transform of 11. Well, let's make that 11 times the Laplace transform of 1. And then here we have 5 times the Laplace transform of e to the 4t minus 6 times the Laplace transform of sine of 2t. All right, and now since we've already done these, we should be able to do this fairly simply. So the Laplace transform of 1 is 1 over s. So 1 over s times 11 is going to be 11 over s. Again, s has got to be greater than 0. And here we have e to the Laplace transform of e to the 4t. Well, that's going to be 1 over s minus 4 times 5 is going to be 5 over s minus 4. And s has got to be greater than 4. And then for this last one, the Laplace transform of sine of 2t is going to be 2 over s squared plus 4. And then multiply that by 6, we're going to get minus 6 times 2 is 12 over s squared plus b squared, which is 4. And again, s has got to be greater than 0. So notice that all of these are valid as long as s, all of these are defined as long as s is greater than 4. And so we're gonna put the stipulation here that s has got to be greater than 4. That way, all of our terms, all of our Laplace transforms are valid here. So this will be the answer for the Laplace transform of this expression. For this next example, we're given this handy-dandy table of Laplace transforms, which includes the Laplace transform of e to the at times t to the n, where n is a natural number, is equal to n factorial over the quantity s minus a to the n plus 1 power, as long as s is greater than a. And the Laplace transform of e to the at times cosine of bt is equal to s minus a over s minus a quantity squared plus b squared, again, as long as s is greater than a. And then we're asked to find the Laplace transform of this here. So just as we did in the last example, we're going to split this up. We're going to bring this constant out front. So this is equal to 5 times the Laplace transform of t squared e to the negative 3t minus, there's no constant here, but this is the Laplace transform of e to the 12t times the cosine of 8t. So we're going to use what we already know up here. Here we're going to use this one, and n is going to be 2, and a is negative 3. So this is equal to 5 times 2 factorial over s minus a to the n plus 1. N is 2, so n plus 1 is 3. And then here, 5 times 2 factorial is just 2, so 5 times 2 factorial is 10. And here, s has got to be greater than a, which is negative 3. And then minus the Laplace transform of this expression. So we get e to the 12t times cosine of 8t, that's this, with a equal to 12 and b equal to 8. So we're going to get s minus a, which is 12, divided by s minus a squared plus b, which is 8 squared, so that's 64. And here, s has got to be greater than a, which is 12. And so for the whole thing, in order for this entire expression to be valid, or to be defined, s has got to be greater than 12. So we're going to put that here, s is greater than 12. And there is our Laplace transform for this whole expression. All right, finally, I want to say a few words about the conditions for the existence of a Laplace transform. In order for a Laplace transform to exist, the function has to be piecewise continuous on the interval from 0 to infinity, and it can't grow faster than an exponential. So I want to just talk about piecewise continuity and what that means. So this third example says, it gives us this piecewise function and says, show that this is piecewise continuous on the interval from 0 to 3. So let's graph this, see what this looks like. From 0 to 1, let's call this 1, 2, and 3. From 0 to 1, this is going to be just a line with a slope of 1. We'll put some circles here at the endpoints to show that the endpoints are not included on this line. Next, we have 2. So we're going, we just have a horizontal line from 2 to 1, or from 1 to 2, from t equals 1 to t equals 2, a horizontal line at f of t equals 2. And then for this third one, this is a parabola, just a t squared parabola, shifted over 2. So we're gonna start here, and this is going to be a closed circle because we're including the endpoints on this last one. And it's going to end up here at 3, and it's going to curve up in a parabolic shape like that. So we can see that between 0 and 1, between 1 and 2, between 2 and 3, that these are continuous functions. Now, what about at t equals 1 and at t equals 2? Can we say that this is piecewise continuous on the interval from 0 to 3 inclusive? And the point here is that, remember, for continuity, we said that something is continuous as long as both of the one-sided limits exist and they're the same. So in order for this to be continuous at t equals 1, for example, we can see that the limit as t approaches 1 from the left is 1, and the limit as t approaches 1 from the right is 2. So we would say this is not continuous at t equals 1. But for piecewise continuity, all we care about is that the one-sided limits exist for every point on that interval. So we can look at every point on this interval, including 0 and 3, including 1 and 2, and we can see that the limit, the one-sided limit, exists everywhere, and it's a finite point. It's not infinity anywhere. Piecewise continuity doesn't include a point where there's going to be an infinite discontinuity. But for these jump discontinuities, this is going to be piecewise continuous as long as every point on that interval has a one-sided limit that is a finite number.